Please pause the video and take a moment to read this important safety message. Okay, I decided to make this a separate video for a couple reasons. One, the video was getting long leading up to where we are in step 5 here of the Scott 210Fs, but more so because the steps I'm about to show you apply to a lot of Scott amplifiers, not just the 210Fs, and there's a lot of mystery out there, it seems, around these. And I thought I would do my best to kind of demystify this a little bit. So let's dive in. Okay, I think it's fundamental that you understand what's going on with the output circuit on this Scott amplifier before we go over to the bench and start turning screws. So this is just a snippet from the larger schematic, and this is the section focused solely on the output. You've got the two EL34s right here in a push-pull configuration, okay? And this is a fixed bias amplifier. So what that means is when this amplifier is playing, the cathodes are grounded. So at most times when the amplifier is playing, these two little wings right here are locked down and closed, which means the cathode current flows out of it straight up through here, straight through this wing, straight to ground. Same out of this one, straight to ground. So during most operation of this amplifier, there are no resistors in the cathode and the cathodes are grounded. So based on that, you've got to pick up your negative voltage on the grid somewhere else. So I showed you that earlier. We've got the minus 51 volts here coming from our negative supply that was being provided by the selenium rectifier, and we replaced it with a modern solid state rectifier. But this is where we pick up the negative voltage that ultimately feeds up through this 2200 ohm resistor, through this balance pot here, okay, up and into the grid of this tube, down and into the grid of this tube. So that provides our constant negative grid voltage to bias these tubes properly. Okay, next I'd like you to understand the purpose of these little wing terminals here that are on top of the amplifier that actually make it easy to access, okay? When you unscrew these outer two screws and loosen the center screw, you can then swing these wings out of the way, in essence breaking the connection here from ground to through these wings. And what happens then is, in essence, you're putting into play two 27 ohm resistors that are normally not in play. In other words, your cathodes now feed down. Keep in mind, this is an open circuit over here. There's nowhere for current to flow. In other words, it has to flow through this 27 ohm resistor down to ground. Same here, out of this cathode through the 27 ohm to ground when you have opened these two wings up on the top of the amplifier. And these are just considered test points. So at this point, what we've done is inserted a 27 ohm resistor in this cathode, a 27 ohm resistor in this cathode, both tying to ground. It gives us a place to measure across. It is somewhat insignificant in its value to how the amp operates. You wouldn't want to leave this long term, but in the short term, it's fine to unconnect these and use this to make measurements with. Now, if you think about it, it's very important that these two 27 ohm resistors are equal. If one of these was, let's say, 25 ohms and the other was, say, 30 ohms, and you were measuring across these and you were making adjustments over here with these three potentiometers based on the value of these, you could get your signal out of whack, and one tube would be driving stronger than the other tube in a push-pull configuration, which equals distortion. Okay, once you've verified these two resistors are equal value, and if they're not, please swap them out and make these equal. It is very important in the biasing process. Keep in mind, these are old common carbon comps. They drift up in value over time. They may not be equal. Doesn't matter exactly so much if they're 27 ohms. You know, they could be 28 ohms. They just need to be equal on both sides here. Okay, let's take a look at the three potentiometers on top of this unit and how we will use them to set the bias properly on this fixed bias amplifier output section, okay? First, you've got this blue circled area here. This is the overall bias adjust, okay? Remember, we had a negative supply made up of that selenium rectifier that we replaced with a solid state rectifier, and it was feeding 51 volts negative right here. I'll say ish because we were feeding a little bit more than 51 volts, but that's okay. It's what this potentiometer's for. This potentiometer plays one role and one role only, and that is a voltage divider, okay? It determines how much voltage to send over here through ground, through this 27 ohm resistor, versus how much to send up here through this potentiometer up into the negative grid of this tube and down into the negative grid of this tube, okay? So in other words, we could adjust this all the way probably from somewhere around minus 50 volts, and if we turn it the other direction, probably down to minus 30 volts. And that will determine the overall bias set on these output tubes right here. Now, Scott's recommending minus 40 volts, so that's what we're going to shoot for. Okay, up next, we have the DC balance pot. Okay, keep in mind, there could be things about this circuit over time that have drifted. In other words, maybe this 150K ohm resistor has drifted up to be 155K, and let's say this one over here hasn't drifted up any. So you've now got an imbalance between these two. Thus, you would end up with a different voltage on the grid of one tube versus the other tube. Thus, they're not biased the same. Thus, you get distortion on the output. Or, could be that these tubes aren't matched very well, and the voltage drop you're getting across each of these tubes isn't equal, okay? And thus, the voltage you would be reading here on the output across these two resistors wouldn't be equal because the current flowing through them would be different. Thus, you would have distortion. So in other words, this is all about balancing the amount of DC flowing into these tubes to make sure it's equal. And we care more than that about them just being equal on each tube. We care about them being equal on the output here. In other words, we want the plate current flowing through these tubes, which ultimately, once it flows through the tube, becomes the cathode current. We want those currents to be the same. Then both tubes are putting out the same amount of output, if that makes sense. So what we're going to end up doing is measuring the voltage across these 27 ohm resistors, and we want them to be as close to each other as possible. Now you understand why having these resistor values equal is so important. So if we're measuring across this 27 ohm and we measure a voltage, and we measure across this 27 ohm and we measure the voltage, and they are equal, then we are driving these tubes equally. We are creating the same plate current through these tubes. Thus, these tubes are biased equally. And this DC balance pot will help us do that. Think of the blue one as how hard we're going to drive these tubes. Think of this green one as how equally we're going to drive these tubes with the amount of drive determined by the blue pot. Okay, I need you to understand, up to this point, everything we have talked about has been about setting the DC conditions around these output tubes. We're adjusting this to make sure we have the same current flowing through these based upon the same voltages feeding to them. All these are DC current, DC voltage, okay? However, this little pot right here plays in the middle of this phase inverter where we split the signal out that feed these two output tubes, okay? And this little pot starts to take that, what should be a perfectly symmetric split signal, and it starts adjusting. One of these is a little larger than the other, one of them's a little smaller than the other. So this pot is all about how much signal, AC signal, we're driving into these tubes that gets split in half, okay? So ideally this pot would be balanced and we wouldn't have any separation and so on and so forth, but it does give you this adjustment ability if you need it. All right, let's talk about how we will adjust these three potentiometers on top of this unit to bias this amplifier, okay? First step, we're gonna set the DC balance. That's important. Before we can set how hard we drive these tubes, we wanna make sure that we're driving them equal, regardless of how hard we're driving them, okay? And if you kind of use Ohm's law and think about it here, okay? If you know the resistance value and they're equal, and we can get the voltage drop across both of these equal, then the current flowing through the cathodes to ground here would have to be equal, all right? Regardless of how strong or weak or balanced these tubes were, if we get these currents equal, the plate current flowing through them down through to ground must be equal, and that's what we're after, okay? So if we go to the factory steps, which by the way, I have not been able to find a manual anywhere for these 210Fs. So there isn't a factory way of doing it that I've been able to find. But if you pulled what was coming out of another Scott manual of a similar type amplifier, it would tell you to connect a resistor across the output, connect a scope across the resistor, set the horizontal selector to line, remove the phase inverter tube, adjust the DC balance pot for a minimum 120 Hertz response on the scope. I'm going to show you an easier way, which I just did. Ensure these cathode resistors are matched. Adjust for the same voltage drop across each. Remember, I is equal to V over R. Thus, if you've got V and R the same, then I must be the same. And we'll show you here on a bench in a minute. Okay, on to setting the overall bias. If you happen to connect the straps back, you need to disconnect them again, okay? Connect a voltmeter across the center and the left terminal, and then do the same for the right. So you're kind of balancing between these two tubes here. If they are different, go back to step number 1, okay? Measure. You're measuring across a 27 ohm resistor, right? And we remember again, I is equal to V over R. Adjust the bias pot for the desired bias current. And I'm telling you, I think I want these at about 38 milliamps a tube, right? So 38 milliamps at roughly 450 volts provides you a roughly 16 watts out, and that's what the specs were on this. So then, V is equal to I times R, thus 0.038 milliamps times 27 ohms equals to 1.026 volts. So we just want to get to where we're measuring center to left terminal, 1.026 volts, center to right terminal, 1.026 volts. All right, so you may wonder, where the heck did I come up with this 38 milliamps at? Okay, well, there's a lot of good bias calculators online. There's Weber's. This is the one on Rob Robinette's website. There's plenty of them out there. You scroll down till you find the tube you want. You measure the plate voltage on the tube. I just went from ground on the power supply over to pin 3 of the output tubes. I measured 450 volts. I do calculate here. It gives me results, okay? It'll tell you for a class AB, which is push-pull, which we're running here, that it depends on if you want to run it cool. You could run it cool here. You could run it hot over here at 38.9, but right here also, you notice it says Merlin Blinkow believes that up to 85% is okay for class AB fixed amps. I like to run them somewhere around this 70%, and so I was putting in the 38 milliamps. That you could run this amp even cooler at 33, but the good thing about the 38 is that's what gives you the 16 watts out on each tube there, okay? And step number 3 here, the AC balance, says you must use a distortion meter and adjust for minimum second harmonic drive to max output. Okay, what if you're saying, I don't have a distortion meter? Well, here's the good news, the alt way. If your tubes are close to being matched, so in other words, you bought a matched pair of output tubes, set the AC balance pot in the middle and forget it. All right, so what this article basically says on H.H. Scott's website, it does mention the 210. It mentions that this whole system is based on a floating paraphase phase splitter. And basically what it says here, if you read it all, is get you a low distortion signal generator, drive these amps to maximum output, measure the output, and adjust for minimum distortion. In other words, most symmetrical signals feeding into it, okay? If you don't have that distortion analyzer, basically it tells you here, don't worry much about performing this. Set the pot in the middle so that it's balanced and forget about it. Sorry for the long-winded 14-minute explanation up to this point, but I felt it was important that people understand these Scotts. I can't even tell you the number of posts I see online where people really don't understand what they're doing and they're asking questions, and the responses people give back are the right responses in a lot of cases, but I was trying to give you the full picture here so you really understand it. Sorry about that if I got a little long-winded. At any rate, let's get over on the bench and do what we just said. Okay, I've got the unit on the bench here. I do not have it powered up right now. I'm going to turn my multimeter here to ohms. And if you'll notice these little wing connectors we're talking about right here, I've unloosened them already. I'm going to swing one of them around and make sure these get in the very middle and are not touching either side here, okay? And I'm going to use my voltmeter here, my ohm meter here. And I'm going to measure across here. What have we got? 26.4-ish ohms of resistance right here on one side. Okay. And the other side, I've got 29.6. That's a problem because I've got matched tubes. Remember, all that I is equal to V over R, and we're wanting the V and the R to be equal here. Well, I can't make that happen with these resistors that are in it. So I flip the unit over. Let's zoom in a little bit. And right here, on this output tube, right here is this little 27 ohm resistor. And right here is this little 27 ohm resistor. And basically what happens is when you lock down these wings over here, you are bypassing these with a straight short, okay? But as we could see earlier, both of these are out of balance. I'm going to swap both of these out. Okay, I've got them both swapped out now, and if you can see here, I'm picking up 27.2, 27.2. That I can live with. Okay, got my voltmeter on volts now. If you'll notice here, we've got 3 pots on the top. 1, 2, 3. And this little chart right here on the back of the amplifier, thank goodness for this being here. I would have had to reverse engineer it. Anyway, this one says bias. In other words, this is your overall bias drive. Okay, it says here, this is the AC balance. This is the one you would just sit in the middle. And then DC balance, which will be this one right here. This is the one we're going to adjust at this point in time. We're going to do that by measuring the voltage across this and this. So right here, what do we have? 0.585 volts, right? And across the other side, what do we have here? 0.4 something, okay? So we're going to come along and we're going to turn this little pot now at this point. 0.524 on one side, 0.509 on the other. You just kind of keep tweaking it. 0.514 on one side, 0.518 on the other. That's pretty darn close, to be honest. 0.517. Okay, at this point I've been going back and forth. I've got 0.526 on one side. I've got 0.525, 0.526 on the other side. I'm happy with that. Now, both of these tubes have the same current flowing through them because I've got the same voltage drop across those 2 resistors at this point, okay? Now what we're going to want to adjust is the overall drive until we get what we talked about. We want roughly 1 volt across these, 1.026 if you'll remember. Right in there, 1.026. I can live with that. Now, I would go back and check both sides again. Similar, 1.034, 1.023. There again, might want to play with this one to get the balance back in line just perfectly. It's a little bit of back and forth that you play with here until you get both sides right, and then you get the 1.026 out that you're trying to get. Yeah, I'm not going to walk you through the distortion analyzer piece here, because not everyone has one, but for those that don't, it's just a matter of finding the very middle point of this pot, which, by the way, these had red kind of markings on them from the factory where they had been marked, and that's about where it's at. Dead center is where the red marks were. Okay, and when you're done, let's not forget to power the unit back off just to be safe. Swing these 2 wings around and tighten them back down. Keep in mind, at this point, those 2 27 ohm resistors I just put in there, they are completely out of circuit and don't play a role at all, but they were there to help us set the bias, and that's the entire purpose of this. Okay, I've got the unit up on the distortion analyzer at this point. I'm driving it fairly hard right now. And what you can see here is I've got 0.546% distortion coming out of this amplifier. And I'm going to adjust this AC balance pot here and see if I can get that any lower. One direction I turn it takes it up. You notice the distortion's going up. The other direction I take it is taking the unit down. 0.527 is the lowest I've seen. 0.5, it's as low as I can get it right in there. And then it starts going back up the other direction. Somewhere here around this 5.2, somewhere right in there is as low as I can get the distortion on this unit, okay? So that was pretty close to center. We weren't far off. I mean, we're splitting hairs if we're talking 0.52% distortion versus 0.5455. We're going to leave this little unit somewhere right along in there and call it happy. So as you can see, leaving that bias pot in the middle didn't take us far off. Beautifully nice symmetric signal here. Hope this makes sense. Okay, I was putting the feet back on this unit, and one thing to notice, they do have 2 long screws and 2 short screws. The short screws both go on this side, the same side as the record compensator switch. The reason is there's some lines that run from the front to the back, and if you use the long screws, it would eat into those lines. And so the long screws go on the other side of the unit. But I have no idea why they didn't just use 4 of the same size shorter screws. The longer screws add no values. But hey, it is what it is. All right, both units are done. Both units are biased. Got them hooked up here to the Clips horns, which are 101 dB. Actually 106 dB, I think. Super efficient speakers. Pretty quiet. About as quiet as any, good solid tube amp would be. Let's hear how they sound. You get the idea. They sound pretty amazing. I've been listening to them now for a few hours. I'm still going to do some phono testing, and I'll just listen to these things for the next week. Anytime I finish up with something of significance like this, I always listen for an entire week. You just don't want cracks, pops, things of that nature creaking up on you along the way. So that's kind of the purpose of it. At any rate, loved how these things turned out. Hope you guys did too. Enjoyed the journey. Hope you learned something about biasing Scott amplifiers, and what you learned there applies to any fixed bias amplifier. Thanks for watching, everybody. Stay tuned. We've got some more fun stuff coming.